Okay, so thank you for having me here today. So I'm very happy to deliver a talk on the open sourcing of the large area multimodal sensing for humanoid with soft skin. So my name is a brief introduction about myself. So I got my PhD in mechanical engineering in Jamaica University 10 years ago, and right now I'm the associate professor at JAIST. It's the Institute of Science and Technology. So don't mess up with the ICE, okay? We have the J there. So with the university, not the research institute. Okay, so my research actually in the intersection of the soft mechanics, biomimetics, and interaction. So we try to create some robot that have enough sensing and awareness of the environment, but also have a high adaptivity to the environment, so that it can offload some complicated computation through the body. Okay, so it's a morphological computation. So, but today I'm not talking so much on the soft mechanics or some interaction here, we're talking about the large area sensing skin in robotics, and so what we have been doing so far, and also our attempt in open sourcing this system. So actually, my previous the previous talk of Professor Yamaguchi already mentioned a lot about the tactile sensing, so I will not repeat again. But as you can see, so the sensing skin can be covered like our entire body, right? So not only the finger, not only the palm, but also the own arm on the body, right? So so large area sensing skin is something also important because it also initiate the social and also task-oriented interaction as well. So the large area sensing skin is considered important. And so as you can see in this slide, we have witnessed many development of the whole body or like large area sensing. As you can see, the very famous one by Gordon Chen, right? As Oliver already mentioned about that, and he already covered the whole robot, as you can see there. So in the Gordon Chen's development, so they have the multimodal sensing, right? Not only touch, but also the proximity as well. And also the iCup robot here, right? They use the capacitance-based touch sensor for covering the whole robot like that. And the recent one using the EIT, right? Electrical impedance tomography for detecting the change of the impedance on the skin, so that they can detect the location of touch and also the depth of touch on the large area of the skin. But you can see here, they can say skin, but sometimes it's still rigid, or even it has a little bit softness. But you can imagine, like, if you see the robot like that, so I believe we still have some resistance, right, into interaction with the robot, because it still have where the rigid part, and it's look not so many friendly, right? So you can see that is the Baymax, right? It's also my great interest in development of the soft robots. And so the Baymax is way different, right, with the robots you see before. So so the Baymax so this one's also I took from the website of Chris, right, on the Baymax Hero. So you see there's it looks like they have the bone like human, right, and it's very soft covering surrounding like that. And you can see the Baymax can, like, I think it can interact very safely to the human, and also they give the high belief, right, from the human to interact with. So how about like makes this really similar one to the Baymax structures, right? So at that time we have the soft skin covering on the body, and also have the tactile sensing, and even more, right? So this is also the objective. So we like to build something very soft and compliant, but in the same time you can change the softness, so it can be actively changed, right? If sometimes you touch the soft one, and sometimes you want to touch a little bit hard one, right? And also we have the multimodal sensing. and also simplify so that it can be open source and can be utilized among the communities. But that's still something very far from that. So today I would try to introduce a little bit on the preliminary development in our lab. Right? So imagine if you have the large, you want to make the large area sensing. So you have to embed a lot of elements, the sensing elements into the skin, right? And this costs a lot in troublesome in the wiring and also durability as well. So vision-based sensing, as the Yamaguchi professor already introduced before, so it's very it can reduce many complications in design and also in implementation. But so far we have seen many vision-based tactile sensing like this, right? Tactile, left side, soft bubble gripper from Alex, right? And also the finger vision as well. But you can see here the scale, right? This mostly for the finger, the arm, right, palm, and that's all. So so how about we also use the vision-based sensing, but this can be scaled up to the whole body, right? So you can use the vision-based sensing for the head, for the arm, for the body, and for the legs as well. So what if we can do is we can utilize this very interesting technology for the whole body tactile sensing. So this is the motivation of our laboratory. So usually, in the vision-based tactile sensing, so you have the skin, right? And also the markers inside, and you have the marker tracking the movement of the markers. You can have one camera, but you also can two, right? If you want a stereo mapping of the skin. But as you know, the robot, the humanoid robot with arms, legs, right? So they have some shape like elongated, right? Or tube or the barrel shape, as you can see here, right? So you can attach one camera there, right? Here to see the marker inside. But sometimes you can see if you have a external contact, so this part, right, can be occluded from the vision of the camera, right? So if you have one camera, probably it's not enough. So our solution is we have two cameras, right? It's placed oppositely like this, right? So if you have some external applied to the skin, and so if you have two cameras, you can try to construct the stereo image of the markers, and eventually you will have the three-dimensional model of the skin, of the whole skin. And if any contact happen there, so you can track it, and no problem. So this is the main the idea. So we already presented in the RoboSop 2019, but we also started 1 or 2 years before that. But go back to the design, the Baymax, as you see there. So we have the bone inside as well, right? If you only have the skin, as you can see here, so it's very difficult for you to integrate it into the robot body, right? Because you need the stiffness for the bone, and you need the strength for the robot as well. So what we propose is we actually have a kind of a transparent pipe, right? And we put connecting two camera with the bone, so you can consider it as the bone. But because you need a space for the camera, right, to see surrounding markers. So that's why you need the transparent pipe, right? So it's actually it causes a lot of troublesome for us because there's many flares and flexion inside, and it's very difficult to get the right image. But thanks to some kind of mechanical solution, so we can finally get a very nice image of the inner skin, right? This is the captures from the upper camera, and this is from the lower camera, right? So that's the whole idea in this development. So we start with the shape, right? With the barrel shape or the elongated shape, hoping that we can scale up to the whole body, as you can see here, right? So because you have the bone as well, so hopefully you can also increase the strength of the robot, but you also can equip the robot with the soft skin, right? And tactile sensing. So this this is the motivation here. So let's go to the fabrication. So so the skin is made by silicon, and we try to fabricate the skin with one molding, right? So because to increase the durability of the system. So how to do this? So we have the inner mold here with many small holes in, and we put some white silicone into the hole first, right? And then when we combine with the outer molds, and then when we pour the silicone one, here we use the dark one, right? And so for one fabrication, we can make a whole soft skin with all the markers inside, right? So this is the inner side of the skin, and as you can see here, and it's very soft, very durable. So this is the first version in 2018, and now we're still using it. It's not broken yet. So it has an amazing durability, as you can see here. So we also open source the fabrication of this, as you can see in the link over there. So you can try to make one based on the direction in the open source website. So this is the principle for the sensor here. So in this case, we call this one is analysis-based method because here we use the 2 camera and the stereo image as well to construct the skin, right? But not only the deformation, we want to calculate the distribution of the force as well, right? So here the solution is we develop a simplified finite element model of the skin, right? So with the skin can be the FEM model can be used beforehand, and when we combine with the deformation from the 3D construction of the soft skin, right? So eventually you can estimate the contact force simultaneously, right? And it can be done real time. So this is the whole story of the analysis-based method. So let's take a look at the video here. So this is for the paper that's accepted by the Transaction and Robotics last year. So you can. So actually we make a robot arm like that. So with all the skin. But here we always show the working the operation of the soft skin, as you can see here. So the 2 images you see over there is obtained from the 2 cameras, right? And also, so there's some contact. You can see the movement of the markers, and based on the 3D construction of the skin, and also the combination with the FEM, so you can contact the force distribution, as you can see here. And so this can be done real time. Now here maximum maybe 10 or 13 Hertz for the 30 FPS cameras, right? So you can see, and you look more, so you can see here how you can interact with it, right? Very much. So it's very responsive to the ND contact, and with a different type of human interaction, so they can. So it's also promising to change. There's one interesting point here is so this one is actually enclosed, and we can change the inner pressure inside by the air hose. So you can see here when we increase, so it's getting a little bit bigger, and now if you touch, you can feel it's stiffer than when with the lower inner pressure, which means when you change the inner pressure actively, you can also change the sense of touch from the user as well. So this is something interesting for the human-robot interaction. Okay, so for the analysis-based methods, so the good thing is that they can provide the high accuracies of the contact location, localization, and also the force. But there's one thing is quite slow, as you can see here, for only 13 Hertz or 50 FPS camera, and it cannot be improved if you use the same kind of computing resources. Because why? We have the FEM model. In this case, we already try to reduce very much the complexities of the FEM model. We eliminate any kind of rotation of the FEM elements. So even that, we still have a lot of burden in computation, and it's very much difficult to reduce. And for this analysis-based method, so it requires a lot of parameters from the cameras and set up for running like that. So it's quite difficult to open sourcing because I'm not sure they can replicate the same model as we had. So in terms of hardware, we already upload, but for software, maybe we think we may have another approach so that it can be easier to use, more friendly for the open sourcing. So let's come to another method, that is a data-driven method. So as you can see here, so we set up an experiment for data acquisition, right? For any kind of touch, and we get the image, and we train a CNN model, right? So it can output you the contact location and also a contact depth based on the database. So you can see here, it can increase up to 30 Hertz for the 30 FPS camera. It's very fast, right? But there's one disadvantage is the data acquisition, right? So you have to set up the experiment to get the data you want. And this for one, so if the data says only one contact, but if you aim for the multi-contact, you need also set up more complicated experiment as well. So due to the very tiring data acquisition based on this method, so we try to create the digital twin of this camera. So as you can see here, we successful in represent the deformation of the skin and also the marker, the shape, the size of the marker as well. So you can see here, the right one, the virtual one, like look very much similar to the real one in the digital model like this. So how to do this? So real software. So Oliver already mentioned, right? So it's an open source simulation open framework architecture developed by France. It's CNRS, if I'm not wrong. Chris is my friend. So we and also Hugo, right? Hugo. So we collaborated with him in this case. So we can create. You can see here the skin, right? And also the marker as well. So this is something different with another platform for vision-based sensing simulation. So we include the mechanical properties of the skin and also the shape size of the markers as well. So everything inside here. And so in the software, so we get all this the contact states like that, right? With the force, velocity, position, contact, and contact depth. And we put in the gazebo using ROS. So it's very familiar with a lot of robotic systems. So in here, so you can use the camera model in the gazebo, and then this is what you get, right? Based on the data from there. So this is the process that we very much hoping that it can be easy to employ by other researchers, right? Because we all utilize on the open source, the software and ROS as well. So something I think is very familiar with a lot of people here. And we also propose a method for construction of the contact depth, contact location based on the TACnet. So this is the deep convolution network. So we provide the SIM, the image from the simulation, and also the labeling from the software, everything in the simulation. So we train the TACnet model with all the simulated images. And next, so in the real case, so we get the real image and we put into the TACnet so that it can predict the contact location, contact force. But as I think as a lot of people here already aware, we have a gap between the sim to real transfer. So if we use the real image for the TACnet, it works very badly. You can see later. So what we do is we train another network called sim to real to sim. Okay, a network here. So this is what is important here is that we try to create the the look like simulated image from the real image, right? So we use the GAN network, generative adversarial network, right? Okay. So we can create the image that look like the simulated one, right? So you try to trick, use some trick here, right? So instead of using the real one, we use the transform one that look like the real image. So and then we put into TACnet, so it works okay. So and so this is some validation, as you can see here in this video. So we also open sources in the GitHub. Not really easy to use now, but we try to make it more completed soon. And the related paper already conditionally accepted by the TRO. So I hope you can read it in the near future. So here, so this is the training process. So not so much time. So here, in this case, we use the virtual image, right? And to fit the TACnet, and you can see, so they can see it's look quite okay. So this is the ground truth one, the right one. But if you put we fit the real image to the TACnet, you can see the prediction and the ground truth is totally different. So it looks like terribly like difference like this. So by using by transform the real image to the look like simulated image before fitting to the TACnet. So with the processor, we can see it works pretty much better than without the real to sim network. So this is the operation that you can see. So it's respond very much correspondingly to the any contact. And now you can see it work with the 120 Hertz maximally for the 120 FPS camera, right? We also test with the multi-contact, 2-point contact, and also we also test the 2-point threshold, right? Something very familiar with the human skin, like how the skin can detect like discriminate 2-point contact, something like that, and also 3-point, which not really familiar, but we also test that. It also work okay with the 3-point contact as well. So and okay. This is how you can see the sensor can discriminate the 2-point contact, right? Of course, as it away is easier to detect, but it's closer, it's difficult to detect as 2 points. But there's one point that I want you to know, that if you increase the stiffness by changing the inner pressures, you also reduce the 2-point threshold as well. So we use the whole body. So we introduce some use case that you can see here. So to push the object with the object to the desired place based on the feedback from the tactile sensor. And you can see here, if something stuck, right, something make contact with that, so it will stop, right, because it can detect the multi-contact as well. So this is for the task-oriented interaction. We also test with the human interaction as well. This is the pushing with one more object at the same time. So you can use this one as interface for human robot interaction, right? So instead of using information from torque sensor or from the current from the joy motor, so you can get directly the interaction from the skin, right? So okay, so you can guide the robot, or if there's some collision between the human and the robot, so it can react as well, right? You can stop, or you can move to the other place. So this is something that you can expect for the social and task-based interaction using the whole body tactile sensing. So here we don't use any complicated control, right? We don't. So we just is all based on the simple PID control for the robot using the whole body interaction. So we also use this one as the input interface, as like you can we use the experiments, collect the data from more than 50 subjects, right, with the many action like lingering, pinching, push, rub, scratching on the robot link, and you can see, and we train the network so that it can detect the many kind of action between the human and robot. Because human, we have many kind of interaction with the object, right? So we try to distinguish that. And one more thing that we try to do now is through the touch. So we try to predict the emotion of the user, right? When you're angry and when you're happy, the way you touch is also different. So this is like a non-verbal kind of this communication, right, between the human and robot. Of course, it's only in this way you only use the sensor. But in the future, of course, we can integrate with the language, with the video and a lot of things, right? So we can increase the human-robot interaction with the touch perception here. So I mentioned about the multimodal sensing. So in this case, I think it's a little bit similar to the finger vision in terms of proximity and tactile sensing. You can imagine if with the transparent one, as you see in the finger vision, you can see outside. But that is for the finger only, right? You can imagine with the whole robot, and if you put the transparent skin, you have a lot of ambient light, right? It creates a lot of noise, so that it's very difficult to get the proximity one. So how to do this one? So in this, for example, this is the robot skin in the opaque state, right? So you can see the markers here. So in this case, you can say, okay, it's in the tactile mode. But imagine you also have the transparent skin, right? So you can see outside, right? As some like robot, like human arm approach, everything you can see here. So the idea here is if you have the skin that can be switched between opaque and transparencies, like actively, right? So you can have both tactile sensing and proximity sensing with the high reliability. So this is what we with the approach. So we use the PDLC film. It's like a polymerized silicon kind of materials that can, if you apply the voltage and switch on and switch off the voltage, so it can change the transparencies, as you can see here. So I'm sorry there's some Japanese here, but it's like in the touch detection, so it will be in the opaque. So the camera only see the markers, and if you switch into the transparency, so the camera will see outside, right? So when you switch like among two states like that, you can expect you have the proximity and tactile sensing the same setup like that. So we try to train the model, yeah, with the proximity and tactile sensing. So for the tactile sensing mode, you see the TACnet is something similar to that I introduced before. So for the proximity one, so we use some kind of technique that can construct the depth based on single camera, right? So this is something. It's not based on. It's not our approach. So we utilize other work, but we can see here with one input. So you can have the proximity, the depth map of the surrounding, and imagine you have two at the same time, right? So you can have more information and more reliable depth image of the surrounding environment. So this is, and we also construct some experiments so that we can do some validation of the system. So I'm not talking about the tactile one because it's similar to what you see before. So this is proximity sensing. So here we actually get actual distance, right, of the object that approaching the robot arm. So we create the robot arm with the skin, as you see here. So we made everything there. So you can see here, there's some like we try to do validation here. And the left side here, so you can see how it can generate, it can output the data, the distance, right, information between the object and the skin. And you can see here, if you this is the validation case. If you approach the robot arm, so it will go away from you, right, and back and forth like that. So this is the video that we made for the paper submitted to RoboSoft for the next year. So that's the paper you can see in the Wix, and also we create the site, the Google site for disseminate this work to the community, and you can see the second link. So this is actual work of the scheme. Let's see. Okay. So this is opaque state, right? So now you have the on the left side opaque, and you can see you can estimate the contact depth or contact location. And the right side, if you have the transparent, you can see you can see the yeah, you can see the change. Okay. Anyway, so we move ahead a bit. So this is the whole robot link, right? With this switchable transparency scheme, and see that this is very much responsive. Okay, so this is the proximity sensing. If you approach the skin, it can give you about the depth, estimated one. And this is for the touch touch action, right? When you put the skin into the opaque mode. So this is soft, right? It's soft. You can you can change the softness by changing inner pressures as well. Okay, so this is some use case that you can see how the robot can react to the with someone go very quickly near to herself. You can reduce speed. She can reduce speed or move to the other place if something. And if you have the very light touch, right, on that, it still can detect as well. And of course, you can use the tactile sensing for doing many things here. So with this technology, so we would like to scale into the whole robot body, right? A robot arm and the chest and even head, like upper body in the near future. We also use it on as an education kit, right? So this is some on the set that we prepare, and we plan to use the intelligent robotics course for the graduate students at our university. So it's less than $100 for the whole system. So we can make several one, and student can practice, and maybe they can have more interest into the humanoid kind of robotics by using this very interesting sensing system like this. Okay, so conclusion. So I can see so what I can also something also of my inspiration is that Baymax should possess the soft skin, or Baymax-like robots should have the soft skin with large area multimodal sensing for fostering the social and task-based interaction. And I believe the Baymax-like robotic mechanisms would be very inspiring for a student to study the humanoid robot. And actually, open sourcing is very much challenging for some for the mechanical engineering guys like us. But we try to do it for both soft and hardware for dissemination this work into the community. And with that, I would like to thank the speakers and also everyone online and offline. Yeah, okay. Thank you.